There is homework due. It's homework number 5. It's due tonight. My plan is to post homework 6 today, and it will be due in 1 week. And these 3 homeworks are problems that you will, similar problems to what you will see on your next test. So today we're focusing on only counting. There are 3 counting techniques I want to go over. We started the multiplication rule, and I'm going to do some more examples. And then we go over a permutation without replacement, a combination without replacement, and that's where we stop. But there are also permutations with replacement, permutations of non-distinct objects, more counting techniques, but I will focus on just those 3 and give you problems that I know you can use these techniques to solve. Okay, so just to summarize the first one, the multiplication rule. If there are m ways to do x, m ways to do one thing, and n ways to do a different thing. I'm just going to put n. Then you multiply those together to know how many ways to do both x and y. And in that order, x and y. Okay, the first one we look at is a experiment where you flip a fair coin and then you roll a die. And then talk about all possible outcomes from that. So it's not really going to affect the problem when all we're doing is counting, but just, when you look at probabilities, you do want to know if you're what the chances are of either side of, I guess, the piece, like the coin or the die. So we're just going to say it's an unbiased die. It's kind of out of habit. We're going to make a placeholder for the coin and then one for the die. And for a coin, there are 2 ways to flip that coin. It's going to be heads or tails. H for heads, T for tails, which is 2 choices. For the die, you can do 6 ways to flip your die. Either it was a 1, or you roll 2, or 3, or 4, or 5, or 6. And then for those choices, we multiply them together to know how many ways to do both. Okay, we're going to start what the tree diagram would look like, but then move on to a different experiment. Okay, so you start, and the first thing you do is flip a coin. You can have heads or tails. After that, you roll your die. So you can roll 1, 2, 3, 4, 5, or 6. And same here. Let's say you roll the tails, and then you flip a coin and get tails, and then you roll the die, and you can have 1, 2, 3, 4, 5, or 6. And so you would go along each branch to get all 12 outcomes. A heads then 1, heads then 2, heads then 3. Maybe you're here and you go tails 1, tails 2, tails followed by 3. And you'll find a way to represent the sample space. In the next experiment, you flip one coin 7 times. How many outcomes are possible? I'm going to do 7 trials, and so I'll have 7 placeholders. On the first trial, I have a flip, which is a choice between heads or tails. So 2 choices. And then here is another coin, heads or tails. So it's another 2 choices. You're multiplying these together. And that's coming from heads or tails. Same for this one, and this one, this one, this one, this one. All choices of heads or tails each time. And what you have is 2 to the 7th, which I'm afraid to share was 128. So this tree would be very tricky to draw. We're not going to try, but you would split off heads or tails, and off of each branch split again, and then keep on branching off until you get, I think, too many to draw, about 128 outcomes. Okay, next experiment. Okay, I do want to do one more. We are going to have a password made up of 3 digits followed by 4 letters. How many passwords are possible if no digits and letters can be repeated? Yeah, I guess that's how it's supposed to be worded. Okay, 3 digits, 0 through 9. And 4 letters, A to Z. How many passwords are possible if digits and letters can be repeated? Cool. Whew. So first is we need a place for 3 digits and then a place for 4 letters. So I'm going to draw my little spaces. Right, 3 digits followed by 4 letters. For your first place, you have a choice between 0 through 9. I'm going to scoot these down. It's right here. It'd be 0, 1, 2, 3, 4, 5, 6, 7, 8. After counting, that would be 10 options. Okay, and then for the next part of your password, you're using digits 0 through 9, and you can still use all of the digits. It's it's okay if you repeat one of these. So again, 10 choices. And then since numbers can be repeated, the same 10 choices. All right, now we're at letters. For the letters A through Z, A, B, C, X. There are 26 letters in the alphabet. So 26. And then you can choose from all 26 again. And you can repeat letters. So we have 26 choices here and here. Okay, after multiplying everything together. Let's see. 4 456,976,000. Or possible passwords. Okay, for the two other counting techniques, we need to talk about factorials. So factorial is a way of multiplying numbers, but let me just wait till we get a definition. All right, so the factorial. Of lowercase n is written like this. Oops, nope. It's a little n. And this symbol is supposed to be factorial. It looks like an exclamation point, but mathematically read as n factorial. And it is the product of all integers between 1 and n. Okay, so again, one more way of writing this, but mathematically, is to take n factorial and it's equal to n multiplied with n minus 1 multiplied with n minus 2 until you get down to, if it's included in the problem, something like 3, 2, 1, those last few integers. Okay, let's do this. I think we're going to do a bunch to get some practice. 1 factorial is 1. 2 factorial would be 2 times 1, just 2. 3 factorial. So we take 3 times 2 times 1. 6. Okay. The next one we're going to do, but I'll work it on the next board, on the next slide, is 4 factorial. Okay, so using this really quickly, 4 factorial is the product of all integers between 1 and 4. So we're going to multiply 4 with 3 with 2 until we get down to 1. Let's see, this would be 12. It's 2. It's 24. Okay, skipping to 7 factorial. We're going to take 7, multiply with 6, then 5, then 4, then 3, then 2, then 1. I got 5,040. Okay, one more. 9 factorial. Multiply 9 with 8, and 7, and 6, 5, 4, 3, 2, 1. And I got 362,880. Okay, and then one more, but it's more of I thought it was a definition, but then I saw that there was a proof. So it makes me think that it's just maybe we'll call it a fun fact. But if you happen to have 0 factorial, I want you to know that it's equal to 1. And again, there's a way to prove that. We're not going to worry about it though. Just if you come across 0 factorial, just try to have it memorized maybe that it's equal to 1. Okay, let's talk about permutations and combinations like shorthand, and then we'll do the full definition for each. In a permutation, let me see. Combinations order doesn't matter. Permutations order does matter. So when you're trying to unlock something and you have to put the code in order, like on your locker, those really should have been called permutation locks, not combination locks. Because with permutation, that order you put your code in, it matters to unlock your lock. Okay, let's write it down. Permutations the order matters. So if you, let's say you have some event AB, it's different than the event BA. If it's a combination, the order doesn't matter. So this time AB is the same as BA. Okay, so let me give some quick examples of this, but we're going to do actual examples once we do a full definition for each. Let's say what's coming to mind for a combination is to say this is the scoops of ice cream, and you can have a chocolate scoop and a vanilla scoop. It's the same as having a vanilla scoop with a chocolate scoop. It's, either way, you get one of each flavor. Let's say over here, though, we're talking about people who are running for office, and you have a president and a vice president. It's not the same as that placeholder. Let's say the first place is for president. And then the second place is vice president. And having person A in that spot is different than having person B in that spot. So here you have person A is the president, person B is the president. It's a different situation. Okay, we'll do more examples, like actually work them out together once we go over this definition. So for either of these, you have a group of objects, and you select a few objects from that group. Here, the selection order matters. Here, you just take any few objects out of the total. Okay, so permutation is an ordered arrangement. Let's see, I actually just put ordered selection of R objects chosen from N objects. Okay, so you got N total, and you want to choose R out of that set of N, and you are making that choice in order, like the first choice, then the second choice, then the third choice. It's specific. For the notation and the formula. So we're going to find the number of permutations. Of the R objects chosen out of N objects. Okay. And it is, first of all, it's written as a subscript N out of N total in a capital P for permute, N permute R, another subscript R. So this is read out of N objects, permute R objects, select R objects out of the total in a certain order. The formula is N factorial over N minus R factorial. Okay, we're going to do two quick examples of just using the notation. We'll come back later and do like a full experiment kind of thing. We are going to find 5 permute 2. Out of 5 objects, I want to pick 2, and their selection is going to be in a certain order. We take 5 factorial in the numerator. Put it over 5 minus 2. This is 5 factorial over 3 factorial. Let's keep working on this. Expand the numerator. It's 5 times 4 times 3 times 2 times. And then same for the denominator. And then a number over itself reduces to 1. Here and here. So it's 5 times 4, which is 20. Find 6 permute 1. Six permute 1 would be, this goes into the top, 6 factorial. Divide by the 6 right here, and then subtract that 1. It's got a factorial on the outside. All right, 6 factorial over 5 factorial. So we'll expand 6 times 5 times 4. And the same thing here. And then 5 over 5, 4 over 4, 3 over 3, 2 over 2, 1 over 1. What's left is 6. There are also permutation and combination calculators on Google, but it's still useful to know how to use the formula. All right, so we're going to go over the definition for combination and then keep on doing examples for the rest of class. Okay, again, we have a group of n objects, and we select a few out of the group, but this time the order doesn't matter. It's just a random selection of any old objects from the And by the way, for permutations, the selection is without replacement, which means when you've, let's say you're choosing three, or let's say you're permuting 3 items out of 5 items. You pick your first one and you don't put it back. And then you pick a second one and then you pick your third one. No one was put back into the group. You just take all 3 out of the group. Same thing here. When you're grabbing a random selection of R objects out of N objects, you pick one, and then you randomly pick another. You don't put anyone back into the group. You just keep on selecting and pulling them out without replacement. The number of combinations. Of the R out of N objects. Is, and there's 2 ways to write it. I'm going to show just one way so we don't bring up confusion. The way the book goes with is similar to the one before. You have your subscript out of N, capital C for choose. Choose R. It's a subscript. And choose R. It's N factorial. Over R factorial multiplied with N minus R factorial. Move this over. And choose R. It's N factorial divided by R factorial multiplied with N minus R factorial. Okay, we start with 9, choose 4. Nine, choose 4 is 9 factorial over 4 factorial multiplied with 9 minus 4 factorial. 9 minus 4 is in parentheses. So there's 9 factorial and it's divided by 4 factorial multiplied with 5 factorial. Okay, we're going to keep on working on this by expanding the numerator, and then we're also going to do the same to the denominator, and I'm going to keep each of these values in parentheses. All right, 9 factorial. It's 9 times 8 with 7 and 6, 5, 3, 2. Okay, 4 factorial. 4 times 3 with 2 and 1. And 5 factorial. 4 times 3 is 2. Okay. I'm going to focus on this piece and the numerator. So there's the 5 over 5. And then a 4 over 4. 3 over 3. 2 over 2. 1 over 1. All of that simplifies to 1 each time. 4 over 4 is 1. 3 over 3 is 1. Let's see what's left over. No, that's all that's it. That's all that I need. They don't really need to multiply by 1 because it's going to keep the number the same. So I'm going to leave that in the denominator. For the 3 times 2, which is 6, we'll have reduced with the 6 in the numerator. 8 over 4 would reduce to 2. So I've got 9 times 2 times 7. It's 126. Just to get used to the formula, we want to work on simplifying 8, choose 2. Okay, out of 8, we want to choose 2. And the number of options are 8 factorial, divide by 2 factorial. That's multiplied with 8 minus 2 factorial. So far, it's 8 factorial over 2 factorial multiplied with 6 factorial. All right, and I did work on like simplifying this by expanding the numerator, expand all of those factorials. We've got 8 times 7 times 6 times 5 times 4 with 3 and 2 and 1. And then 2 times 1 is 2 factorial. 6 times 5 times 4 times 3 is 2 times 1. I'm going to focus on this part, the second pair of parentheses, and the numerator. And there's a 6 over 6. That's 5 over 5. 4 over 3. 2 over 2. 1 over 1. That's just 8 times 7 over 2 times 1, or just over 2. And then the 8 over 2 is going to be 4. 4 times 7 is 28. Okay, so sometimes, or most times maybe, when you can use permutations, you could also think through the problem using the multiplication rule, but you have to be careful with the choices you make. So with this example, I'll explain 2 ways to solve the problem. And then it's just, your preference on which way you like better. At a swimming competition, or just let's say swimmers compete in a race. How many ways can they place as first, second, or third? Okay, so the first way we're going to do it is with the multiplication rule. There's a first place, a second place, and a third place. So I'll make placeholders. This is where you have your first place, followed by the second place, and there's third place. Oh, we need a number of swimmers. So there are going to be 9 swimmers. Competing in this race. So when the first person goes through the, finish line or something like that, there's 9 options to start with. Now, one of those people has first place, and out of our group, we've taken that person out, and there's 8 people to choose from to give to second place. Now that first place person's removed, there's a second place person out of the group, and there are 7 people left to pick from for third place. And then 9 times 8 times 7. Is 504. Okay, the other way is with permutations. You have a set of 9 people. From those 9 people, we're going to choose 3 people. And we're choosing them in an order. We're going to choose first place, then second place, then third place in that order. So it's a permutation of 3 options out of the 9 swimmers. Out of 9 swimmers, we want to permute 3, choose 3 in a certain order. It was 9 factorial. Divide by 9 minus 3 factorial. 9 factorial over 6. It would be, let's put this. 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Down here, expand 6 factorial. And then the 6 over 6 reduces to 1, 5 over 5, 4 over 4, 3 over 3, 2 over 2, 1 over 1. What's left is this part, 9 times 8 times 7. Which was the same thing we set up after kind of thinking through the multiplication rule. 9 times 8 times 7, which was 504. So either way, you'll get the same answer. It's just how you kind of want to think through the problem. Okay, the next one. You have 5 prizes to randomly distribute to a group of 21 people. And it's only 1 prize per person. So you can't give more than 1 prize to any person in the group. Or maybe it's 1 prize per person. It's better. How many ways can the prizes be given out? Okay, so we've got a set of 21 people, and you want to pick 5 people to give prizes to. It doesn't matter what order you hand these prizes out, just as long as those people each get a prize. So since order doesn't matter, we're going to use combinations and pick 5 people out of 21. See, it's your total of 21, And we want to choose a random 5 people to give prizes to. So we take 21 factorial, divide by 5 factorial, multiplied with 21 minus 5. Okay, so I did one more step, but then I just used a calculator. I want to mention 2 places where you can find values of permutations and combinations once we kind of work through this one. It's 21 factorial over 5 factorial times 16 factorial. Which is 20,349. Okay, well, I mean, you can also just Google. You can just type into Google something like 21 choose 5, and it would probably give you an answer. But you can also go to Desmos Scientific Calculator, and you'd be able to type this in, or at least you could type this in, the factorial sign. Okay. Another place I use sometimes is Wolfram Alpha, and again, you kind of write it in. I would write 21 and then the word choose and then 5, and that would also give me a result. It's called Wolfram Alpha. I don't know if it also has calculator as part of the name, but if you go to Wolfram Alpha in the little search box on their site, you can type in almost any mathematical statement and it will give you all possible answers it can think of. Okay, or you can just try working everything out by hand using the formula. And then let's try to get a couple more examples in. The next one is a pond that contains 30 fish, and you want to select 7 fish out of the pond. How many ways can you do that? So in how many ways can we select 7 fish from a pond that contains 20 fish? Okay, so it's a random selection, any 7 fish. The order doesn't matter. I'm just going to grab a group of 7. It doesn't matter what order they're in. So we're using combinations. from the 30 total, we want to choose 7. And that group of 7, doesn't matter what order they're in, it's just got to be 7 fish. That would be 30 factorial. Divided by 7 factorial. And then 30 minus 7 factorial. Which is 30 factorial over 7 factorial. And 23 factorial. Okay, well, I just put this in and got the result. It is 2,035,800 different ways to pick 7 fish from that pond. Okay, cool. I think we have time for one more example. It's going to have 2 parts. And then I had a few more examples, which we'll either do next week or we'll do during review week. So we're looking at a it's a lock that has 4 rotating discs, each with the numbers 1 through 9. Okay, how many different codes are possible? And then we have part A. For part A, numbers cannot be repeated. Or actually, we're going to start with the can be repeated. A number can be used more than once. So I forgot to write it down when we did the permutation definition, but for permutation, it's a permutation without repetition. And same for combination, it's a combination with no repetition. So if you do see that you can have repetition, you're probably going to use the multiplication rule. So for that rule, we have our spaces, 1 space for each disk. And then they have the numbers 1 through 9. I'm going to move these down. So you can choose 1, 2, 3, 4, 5, 6, 7, 8, and 9. So there's 9 choices. And then you go to the next disk And you can use any of the digits again, because you can repeat the same number if you want to. So another 9 choices, and 9 choices. So this is 9 to the 4th, which would be 6,561. Oops. Part B, if your numbers cannot be repeated. So there's 2 ways you can do these. One is to carefully use the multiplication rule. The other way is to use a permutation, to think that out of 9 digits, we can permute 3 digits to create a code. So the first way is the multiplication rule. You put your placeholders for each, rotating disk. And then you start to make the code, and you choose one of the numbers 1 through 9. So there's 9 choices. But once you pick one of those digits, it can't be used because we can't repeat the same number. So then we've got 8 choices for the next spot. And from these 8, we've picked that number. And so here I've got 7 choices. Now from those 7, there's a number sitting in this spot. And over here, there's 6 left to choose from. It's 9 times 8 times 7 times 6. Which would be 3,024. Okay, another way to get the same answer would be to use permutations. So it's like I've got my 4 places on my lock, and each one gets its own digit in a certain order. So I'm going to take 9 digits and permute 4 of them to create a code. So it'd be 9 permute 4. And that would be 9 factorial over 9 minus 4 factorial. 9 factorial is over 5. 9 times 7, 9 times 8 times 7 times 6. Over 5 times 4 times 3 times 2 times 1. And the 1 over 1 reduces to 1, same with 2 over 2, and 3 over 3, and 4 over 4, and 5 over 5. So what's left is that 9 times 8 times 7 times 6, like we thought through earlier. It's the same answer. Okay, cool. We made it to the end of class. So next week, I will probably do a little bit more about counting, just maybe a couple more examples. And then we want to use counting to find probabilities. So we want to put all of these techniques to use and apply them to probability ideas and experiments. And then after next week, we review for the test and take a test. So, I'm gonna go. Yikes. Bye, guys.